How does a machine find something inside your body years before your own fingers ever could? Picture the room, a cool metal plate. Someone asks you to hold still. And then comes the part everyone remembers. The press, firm and strange, holding you in place. Here is the puzzle. You are made of soft tissue, fat, gland, water. And soft tissue is almost transparent to an ordinary X-ray, the kind that snaps a broken bone in one bright flash. Fire that beam through a breast, and you would see almost nothing. Grey on grey. Nothing to read. So how does a mammogram pull a hidden detail out of something an X-ray can barely see? The answer is not a stronger machine. It is a gentler one. A mammogram uses the weakest X-rays in the entire hospital, on purpose. And it starts with that press you brace for, which turns out to be doing 3 quiet jobs at once. We will take them one at a time, because once you see why the squeeze exists, the whole machine starts to make sense. And it begins with the strangest rule in this field. In breast imaging, weaker is what lets you see.
Why would the best breast scanner in the world use the weakest X-rays in the building? Think back to bone. Last episode, the rule was simple. Heavy atoms stop X-rays. Calcium in bone is heavy, so it blocks the beam and glows bright white. Soft tissue is light, so the beam sails straight through. That is the problem. Fat and gland are both light, both soft. To a strong, high-energy X-ray, they look almost identical. The beam barely notices the difference, and no difference means no picture. Drop the energy down low, and everything changes. Now the beam is fussy. Fat absorbs a little, dense gland absorbs more. That tiny gap in absorption becomes contrast. The soft greys a radiologist actually reads. So the weakest beam is the only one delicate enough to tell soft tissue apart. Now the squeeze. Press the breast flat and 3 things happen at once. Overlapping layers spread out, so nothing hides behind anything else. The tissue gets thinner, so it needs even less radiation. And held still, it cannot blur. The wince is the image quality. But here is the twist. With all that care, the machine still is not hunting for a lump. It is hunting for something far, far smaller, and you would never feel it coming.
What is a mammogram really hunting for? Long before anyone could feel a thing. Not a lump. Specks. Flakes of calcium, smaller than a grain of sand, called microcalcifications. And you already know why they show up. Calcium is a heavy atom. Heavy atoms stop the beam. So each speck lands on the image as a tiny bright white point on a field of soft gray. And a certain pattern of them can appear years before anything is ever felt. That is the scan's real power. It works at the scale of sand, not the scale of a fingertip. But the same physics has a catch. Remember, dense gland tissue absorbs more, so it shows up bright white too. And a worrying spot? Also white. White on white is hard to read. A small thing can vanish into a dense background, like a snowball in a snowstorm. Nobody hides this. It is exactly why density matters, and why doctors add other tools for denser tissue. A 3D scan, an ultrasound, or an MRI, each reading the body a different way. So the physics has a backup, which leaves one last question, the one everyone actually worries about. All these X-rays, how much radiation is that, really?
So, how much radiation does a mammogram actually cost you? People imagine something huge. The real number is almost gentle. A mammogram is about 0.4 millisieverts. And here is a yardstick this channel loves. A banana carries a tiny natural dose of radiation. So the whole scan is roughly 4,000 bananas. Still sounds big? Just being alive on Earth, breathing the air, standing under the open sky. That gives you the same dose in about 7 weeks. A mammogram is 7 weeks of ordinary existence, handed to you in a few seconds. The dose was never the frightening part. The real debate is a different one, and it is honestly unsettled. Catching something early can mean catching it small. But scans can also flag harmless things, leading to more tests and worry. When to start? How often? Doctors and major guidelines weigh those trade-offs, and they do not all agree. That is a decision for you and your doctor, not for us.
Step back, though, and look at what the physics pulled off. For most of history, the rule was brutal. Wait until you can feel it. The weakest X-rays in the hospital, plus a firm press, rewrote it. See it while it is still a speck. That is the quiet miracle inside a cold metal plate. Would you rather catch it as a speck or wait to feel it? Speck or wait? And if you want to know why bones stop the beam in the first place, the X-ray episode is on screen and in the pinned comment. Watch that one next.